Hey guys, it's Miss Riddle. I just want you to know you're in for a real treat. That this video, I'm pretty sure, is going to go viral. It's going to be so good. Lucky, lucky you. Anyway, I'm sorry that I'm not there today. I know I shared with some of you that I am heading to Kansas to participate in the Walk to Defeat ALS in honor of my dad, and I will send you a picture. I'm very excited. It's going to um, be a really cool day. So anyway, sorry I'm not there though, and I don't want you to get behind the other class. So we worked a few more optimization problems, and I wanted to share those with you. So if you look in your notes, you're going to find these. You can pause this for a second if you need to find these, but we will work, I think, two more problems. So your notes are more complete. So first of all, let's just imagine, now this oil is really not sold in cans anymore. Have you noticed that? Those of you that have purchased motor oil before, it's now in plastic. But in the olden days when I was your age, it was in a metal can, like soup. So let's imagine this. So we have a metal 1 liter oil can shaped like a right circular cylinder. And what dimensions will use the least material? So we want to design this can to use the least amount of aluminum. So we know that this can equals 1 liter, but we're wanting to find the surface area. Well, the surface area is not going to be measured in liters, so let's convert that liter into units that makes more sense for our problem, and that would be 1,000 centimeters cubed. So 1 liter equals 1,000 cubic centimeters. The other thing we have to think about is what is the equation for surface area. So obviously we have a top and a bottom, so that's two circles, so 2 pi r squared. And then we have this circular part, which would be the height times the circumference. So the circumference is 2 pi r times the height. So this is the area, the surface area. Well, we also know that the volume of this oil can is, let's think about that. What's the volume? The formula for volume is pi r squared times the height. I had to think about it for a minute. All right, and we know that the volume is 1,000. So we need to solve for one of these variables, either r or h. And personally, I think h is going to be easier. So the height is equal to 1,000 over pi r squared. Everybody okay on that? Okay, so now what I can do is I can substitute this value into my surface area, and then fortunately I only have one variable. So 2 pi r squared plus 2 pi r times, and in place of h, we're going to substitute 1,000 over pi r squared. So cleaning that up a little bit, I can divide the pi's to 1, divide the r's, and then I'm going to get 2 pi r squared plus 2,000 over r. Okay, excuse me. And next, what I'm wanting to do is I want to find the minimum value of the surface area. So we know in calculus we can utilize the derivative to find a maximum or a minimum. So let's take the derivative of this function. So that's going to be 4 pi r plus, and remember 2,000 r to the negative 1 would be negative, I'm going to change that, negative 2,000 over r squared. Okay, now we could try to use some algebra, but I think that's a little crazy. So let's substitute this into y1 in our calculator, and let's find the minimum value. So pause this for a second, put this into y1, and look for zeros. Look for any zeros that you see, and I'm assuming that our radius obviously needs to be greater than 0. So we would need an x value greater than 0, or a 0 greater than 0. Okay, that's repetitive. But go ahead and graph that, and I'll pause it for a second, and then we'll come back and discuss what we found. Okay, so when I evaluate this, I found a 0 at 5.419. So also, when you look at that graph, you can see that the derivative goes from a positive to a negative at 5.14. So we know that this is a minimum. So this is what we would want the radius of our can to be. And then going back to this function right here, the height would equal 1,000 over pi r squared, or 1,000 over pi 5.419 squared. And that would give us the height, okay? Which is approximately 10.839 centimeters. So these two dimensions would minimize the amount of material that I would need for my can, keeping the volume of the can at 1 liter. Okay? All right, so that's the first problem I wanted to work for you. The next problem I wanted to work for you is maximum profit. And I have a typo here. I really feel that this should say revenue. And then, so that's our revenue function, and here's our cost function. Now, let me tell you, I know very little about economics. How I got through school without taking economics, I don't know. But I do understand that profit is equal to the revenue, the amount of money you bring in your business, and then subtracting how much it costs you to either produce the product that you're selling or the cost in offering your services. So the profit is the revenue minus the cost of running your business. So let's take a look at this. We know that the revenue is 9x and CX is our cost. X represents thousands of units, and we want to know what production level would maximize profit. Maybe if our production level is too high, we have to start paying employees overtime, or we have other challenges to trying to make a production level too high, or we have to buy more machinery. And so there could be a point where we're making too many products, and then conversely, there could be an amount of products we're creating where we aren't making enough of a profit. So we want to maximize this profit. So let's call this P of X, and that's going to equal 9x minus x cubed minus 6x squared plus 15x. Okay, and we can simplify that to negative x cubed plus 6x squared minus 6x. Check my math real quick and see how I did on that. So I got negative x squared. I'm checking my work here to see how I did. Yep, I think that looks okay. All right, now let's take the derivative of that because we want to know when there's a maximum. So I get negative 3x squared plus 12x minus 6. Everybody good on that? Okay, so let's set this equal to 0. All right, so what I'm going to do is use my calculator, and I'm going to graph and see if I can figure out where this function equals 0. So you do this, I'm going to do this at the same time, and see what we get. So y equals negative 3x squared plus 12x minus 6. Okay, so I see two values, two x-intercepts, and I'm going to calculate those, and I get x is equal to 0.586 and x is equal to 3.414. Now looking at this, the 0.5860, my function goes from negative to positive, and remember this is the derivative. So that means the function goes from decreasing to increasing. So that's actually going to be a minimum value. So I'm not interested in that. No business is interested in minimizing profit. So this at 3.4, if you look, it's going from positive to negative. So therefore, it's increasing then decreasing, and this here would be our maximum. So in order to make the most profit, the maximum profit would occur when we're making 3,414 units, because our units are in thousands. That would maximize our profit. Okay? And I think that's all we're going to do. This problem we'll skip, but I hope that helps. A couple more examples of optimization problems, and I look forward to seeing you on Monday. I hope you have a great weekend. 3 days. That's not bad. All right, be safe.